Tonight we're going to talk about how much time the universe has left. Not in a vague philosophical sense, in a precise physical sense. The universe has a future that can be described in detail, mapped across timescales that make the current age of the universe look like the first second of a very long day. And when you see the full picture of what cosmologists have mapped out, what emerges is something unexpected. We are living in a brief, bright window. Stars, the galaxies, the planets, the possibility of life anywhere in the cosmos, these are not permanent features of the universe. They are a phase, a thin slice of cosmic history that will eventually give way to an era of darkness and cold, so profound that nothing in our current experience has any analogue to it. The universe is 13.8 billion years old. That number is so large that it tends to feel like a long time, and by human standards, it is. But the universe does not measure time by human standards. It measures time by the lifetimes of its stars, by the evaporation of its black holes, by the slow decay of its protons, and by those measures, 13.8 billion years is not old. By those measures, 13.8 billion years is early. By the end of tonight, you will understand why cosmologists describe the current era of the universe as a special temporary condition. Why the universe as we observe it tonight, full of bright stars, active galaxies, and habitable planets, is already in decline. Why the rate of star formation in the universe peaked roughly 10 billion years ago and has been falling ever since. Why the universe will not simply fade slowly and uniformly into darkness, but will pass through a sequence of distinct eras, each of which is almost incomprehensibly longer than anything that has come before it. We are going to cover all of it. The stelliferous era we are living in, the age of stars and why it has a hard expiration date, the degenerate era that follows, when the dominant objects in the universe are not stars but their cooling corpses, the black hole era, when the last matter has either fallen into black holes or been destroyed by proton decay, and the dark era, when even the black holes are gone, and the universe is a thin, cold, expanding soup of particles and radiation that will never form another structure of any kind. Before we get started, the number at the centre of tonight's story is this. The era of stars, the age in which we live, will last for roughly 100 trillion years. 100 trillion years. The universe is currently 13.8 billion years old, which means we are less than 1/100th of 1% of the way through the stelliferous era. We are, by cosmic standards, not just early in the universe's history, we are almost at the very beginning. And yet, despite that vast remaining future, the conditions that make life possible, liquid water, rocky planets, stable stars, chemistry complex enough to build and sustain biology, are tightly clustered in a much narrower window than 100 trillion years. Most of what will happen in the universe after tonight, after this moment, will happen in conditions hostile to life, hostile to planets, hostile to chemistry, hostile to anything we would recognize as meaningful structure. That is what shorter than you think means in the title of tonight's episode. Not that the universe is about to end in any conventional sense. It is not. It will persist, in some sense, essentially forever. Though the question of what is shorter than you think is the window, the bright, warm, star-lit window in which the universe contains anything worth calling a place. Now let's begin. The stelliferous era is the name astronomers and cosmologists give to the current period in cosmic history, the age of stars. It began roughly when the first stars ignited, perhaps 100 to 200 million years after the Big Bang, and it will end when the last stars exhaust their fuel and go dark. The end of the stelliferous era is not a sharp event. It is a gradual dimming. Stars of different masses live for very different lengths of time. The most massive stars, those with 20 to 30 times the mass of our Sun, burn through their hydrogen in a few million years and explode as supernovae. Our Sun, a middle of the road star, will spend about 10 billion years on the main sequence before expanding into a red giant and leaving behind a white dwarf. And the least massive stars, the red dwarfs, will burn their hydrogen so slowly and efficiently that they will still be fusing in 100 trillion years, long after every star like our Sun has already died. The stelliferous era does not end at a single moment. It ends with the last red dwarf guttering out somewhere around 100 trillion years from now. After that, there are no new stars being born, because the gas available for star formation has been consumed, and there are no old stars still burning, because even the most frugal red dwarfs have finally exhausted their fuel. The universe will contain no star at all. The age of stars, the entire luminous history of the cosmos, will be over. No one expects that statement to land with the force it deserves on a first hearing. We are so accustomed to thinking of the universe as a place full of stars, a place of galaxies and nebulae and all the machinery of stellar life, that imagining a universe with no stars at all seems almost impossible. And yet, that is exactly what is coming. The universe was dark before the first stars ignited. It will be dark again, permanently, after the last star dies. The age of stars is a finite, bounded episode in a much longer cosmic history. We are in the middle of it. The history of star formation in the universe is not flat. It has a shape. It started slowly in the first hundreds of millions of years after the Big Bang, rose steeply to a peak, then began a long, slow decline that has been continuing ever since, and will continue until there is no more gas to form stars from. Understanding that shape, the rise and fall of cosmic star formation, is essential to understanding why tonight's story is not about the distant end of everything. It is about the decline that is already well underway. The peak of star formation in the universe occurred roughly 10 billion years ago, about 3 to 4 billion years after the Big Bang. At that time, the universe was converting gas into stars at a rate roughly 10 times higher than it is today. Galaxies in the early universe were bright, turbulent, actively star, forming systems with far more activity than the comparatively quiet galaxies of today. The Milky Way, by the standards of the early universe, is a sedate, middle, aged galaxy with a modest star formation rate of perhaps a few solar masses of new stars per year. By the end of tonight, you will understand what that declining star formation rate means for the long-term future. But the immediate point is that the universe has already passed its productive peak. The greatest burst of star formation in cosmic history is behind us, not ahead of us. We are in the long declining tail of an activity that peaked while the sun had not yet formed. No one predicts this is intuitive from observation alone. When you look up at the night sky and see thousands of stars, when you look at images of the Milky Way's 300 billion stars, when you read about the 2 trillion galaxies in the observable universe, it does not feel like decline. It feels like abundance. But abundance and peak production are different things, and the universe's peak productive phase is already part of its history, not its future. The reason star formation is declining is fundamentally one of raw material. Stars form from cold, dense gas, primarily hydrogen and helium, concentrated in molecular clouds. The early universe was rich in this gas. It had not yet been processed by generations of stars. But every time a star forms, lives, and dies, it converts some of that primordial gas into heavy elements and returns them to the interstellar medium, but not all of it. Some fraction ends up permanently locked in stellar remnants, white dwarfs, neutron stars, black holes, from which it will not escape on any relevant timescale. Each generation of stars depletes the available fuel slightly, and over billions of years this depletion has measurably reduced the rate of star formation across the universe. At the current rate of decline, the universe's star formation rate will continue to drop by roughly half every several billion years. By the time the universe is 100 billion years old, 7 times its current age, the rate will be so low that only a tiny fraction of the stars forming today will still be forming. scattered. The great era of galaxy building will be effectively over. What will be left in the stelliferous era's later stages is a universe dominated by red dwarfs. These are the smallest stars, with masses ranging from roughly 7.5% to 50% of the Sun's mass. They are so faint and so cool that no red dwarf is visible to the naked eye from Earth, despite the fact that red dwarfs make up roughly 70 to 75% of all the stars in the Milky Way. Because they are so numerous, and because they burn their fuel so slowly, they will outlast all other stars by an enormous margin. A red dwarf with 20% of the Sun's mass will spend roughly 5 trillion years on the main sequence, burning hydrogen through a fully convective interior that constantly mixes fresh hydrogen into the core. The Sun, by contrast, burns through its core hydrogen in 10 billion years, leaving behind an unburned envelope when the core is exhausted. A red dwarf does not do this. It is fully mixed. It will use essentially all of its hydrogen before it dies, and it will do so over a time span that makes the Sun's lifetime look trivially short. The smallest red dwarfs, those with perhaps 8 to 10% of the Sun's mass, will burn for close to 10 trillion years. These are the last stars. They will still be fusing hydrogen when every other type of star in the universe has gone dark. They are the last light of the stelliferous era, dimly red, barely luminous, far too faint to support photosynthesis on any planet in their habitable zones, but still converting hydrogen to helium and releasing energy through nuclear fusion. No one expects red dwarfs to be the obvious heirs to the stelliferous era. They are nothing like the Sun, nothing like the great blue, white, massive stars that produce most of the light in the current universe. But the universe does not optimize for brightness. It optimizes for whatever physics allows. And physics allows red dwarfs to burn for 100 times longer than the Sun, 1,000 times longer than a massive O-type star. They are the universe's most efficient stellar engines, and they will be the last ones running. When the last red dwarf exhausts its hydrogen, roughly 100 trillion years from now, it will not explode as a supernova. It has too little mass for that. It will not become a neutron star or a black hole. It will simply shrink, contracting slowly until it is supported against gravity by electron degeneracy pressure, and cool into a dim white dwarf of primarily helium rather than the carbon, oxygen white dwarfs that Sun, like stars, produce. A helium white dwarf. It will sit there, cooling, for a very long time. At that point, the stelliferous era will be over. The universe will have entered the degenerate era. Before we get started on what the degenerate era actually looks like, there is one more feature of the stelliferous era's end worth understanding. At some point in the latter stages of the stelliferous era, perhaps 20 to 30 trillion years from now, the dark energy-driven expansion of the universe will have isolated the local group, the cluster of galaxies including the Milky Way and Andromeda, behind a cosmological horizon beyond which no future signal can reach us. All other galaxy groups will have receded so far that not even light has travelled between us and them since the onset of dark energy acceleration. The observable universe, as seen from the local group, will contain only the merged remnant of the local group galaxies. Every other structure will be gone from view. The last stars will burn in a universe that, from any local perspective, appears to contain nothing but themselves. The last star deserves its own moment. It is not a hypothetical concept. It is a specific type of object, a red dwarf, and its eventual death can be described with the same precision we apply to the death of any star we study today. The last star will not go out in a dramatic explosion. It will not collapse into a neutron star or a black hole. It will simply exhaust its fuel and contract, slowly and quietly, into a dim, cooling helium-white dwarf, and that will be the end of the stelliferous era. The last star will be a red dwarf near the bottom of the main sequence, perhaps with a mass around 8 to 10% of the Sun's mass, right at the hydrogen burning threshold. Such a star is so faint that if you placed it in our solar system in place of the Sun, it would not heat Earth's surface enough to melt ice. Its surface temperature would be roughly 4,500 to 5,000 degrees Fahrenheit, compared to the Sun's roughly 10,000 degrees. Its luminosity would be roughly 1/10,000th that of the Sun. If you were standing on a planet in its habitable zone, you would need to be about 2 to 3% of the Sun, Earth distance from the star to receive enough warmth, about 3 million miles, close enough to potentially be tidally locked with one face always toward the star. Before we get started on what makes the last star significant beyond its sheer longevity, it is worth noting the sheer scale of its lifetime. A red dwarf at the hydrogen burning threshold will spend roughly 100 billion to 10 trillion years on the main sequence. The precise number depends on its initial mass and composition. Current estimates for the most frugal red dwarfs put their main sequence lifetime at around 10 to 12 trillion years, which is roughly 700 to 850 times the current age of the universe. A red dwarf born at the same time as the Milky Way, roughly 13 billion years ago, will still be burning hydrogen 12 trillion years from now, when the Sun has long been a cold white dwarf, when the Andromeda merger has long since been completed, when even the merged elliptical galaxy has begun to dissolve its outer stars through gravitational evaporation. The last red dwarf will burn through all of that cosmic history and still have fuel left. The fully convective interior of a red dwarf is central to its longevity. A star like the Sun has a radiative core surrounded by a convective outer zone. The nuclear burning happens in the core, and the helium ash of hydrogen burning accumulates there, gradually reducing the fraction of hydrogen available for fusion. When enough helium is built up, the star's core structure changes, and the star leaves the main sequence. A red dwarf, by contrast, is convective throughout, meaning the plasma circulates from the burning region outward and back, continuously bringing fresh hydrogen into contact with the nuclear burning zone and carrying the helium ash away. The red dwarf has access to essentially all of its hydrogen, not just the hydrogen in a limited core region, and it uses it all before it runs out. This is why red dwarfs produce no planetary nebula when they die. A Sun-like star loses its outer layers in stellar winds and eventually expels a significant fraction of its mass as a glowing planetary nebula. A red dwarf at the bottom of the main sequence has so little mass that its gravitational field keeps its envelope bound even as the nuclear reactions wind down. It simply contracts directly to a white dwarf, the planetary nebula phase absent, or so brief and faint as to be negligible. The death of the last star will be quiet. There will be no glowing shell of gas expanding into space. There will be no brilliant flash of light from a newly exposed stellar core. There will be a slow contraction, a gradual dimming, and then a cooling white dwarf where once a faint red star burned. Absolutely no one anticipates being present to observe it. The timescales involved ensure that no civilization arising in the stelliferous era will survive to see the last star die, unless civilization, intelligence, or information processing of some kind manages to persist through the degenerate era on very long timescales. The last star will die in a universe that is, by any reasonable interpretation, already ancient beyond comprehension. The question of whether the last star will have planets is interesting. Red dwarfs are known to host planets frequently. Surveys suggest that essentially every red dwarf in the Milky Way has at least one planet in its planetary system. Some of those planets will be in the habitable zone of the star, close enough to receive adequate warmth. Whether any of the last surviving red dwarfs still have planets in 100 trillion years depends on the long-term dynamics of planetary systems over such extreme timescales. On timescales of trillions of years, planetary systems are subject to slow, gravitational perturbations from passing stars, from galactic tidal forces, and from the internal dynamics of multi-planet systems. The probability of a planetary system remaining intact for 100 trillion years is low, but not zero. The outer planets of a system might be stripped by passing, star perturbations over a few trillion years, the inner planets might survive for much longer, their orbits slowly evolving but remaining bound. It is possible, though uncertain, that the last red dwarf will still have one or more close, in rocky planets orbiting it when its hydrogen finally runs out. Those planets will not be warm or habitable by any standard we apply today. Even the close, in planet of a last surviving red dwarf will receive minimal energy from a star that is itself spending only a tiny fraction of the energy per unit time that our Sun does. The surface of such a planet, if any atmosphere survived the trillion-year cosmic radiation environment, would be lit by a dim reddish glow, and the sky would contain no other stars, or only a handful of other red dwarfs as faint and cool as the central star. And eventually, when the star contracts to a white dwarf, the planet will remain, orbiting a dim, cooling cinder in a universe that has gone dark everywhere else. The very last sunlit world in the universe will eventually be a frozen, airless rock orbiting the dim remnant of the last star. No one expects that to be observed, but as a physical fact, it is almost certainly true. The question of whether red dwarfs can host habitable planets is one of the most consequential open questions in astrobiology. If they can, the universe's stelliferous era is far more habitable than we might initially think, because red dwarfs are so numerous and so long-lived. If they cannot, then habitable worlds like Earth are restricted to a narrow window around Sun, like stars, and life is statistically rarer than it would be if red dwarfs are viable hosts. Red dwarfs present a specific set of challenges for planetary habitability that are quite different from the challenges posed by a Sun-like star. The first and most discussed is tidal locking. A planet in the habitable zone of a red dwarf must orbit very close to the star, roughly 2 to 5% of the Sun-Earth distance, to receive enough warmth for liquid water. At such close distances, the gravitational tidal force from the star will over millions to billions of years synchronize the planet's rotation with its orbit, so that the same face is always toward the star. The planet will have a perpetual day side and a perpetual night side. Whether tidal locking is fatal to habitability is debated. Early models suggested that a tidally locked planet would freeze out its atmosphere to the night side, where it would condense permanently, leaving the rest of the planet airless. More recent models with realistic atmospheric circulation find that the situation is more complex. A sufficiently thick atmosphere can transport enough heat from the day side to the night side to prevent catastrophic freezing. The day side will be hotter than Earth's daylit face, the night side colder, but the transition zone between them, sometimes called the terminator zone, could maintain temperatures compatible with liquid water. Life in such a terminator zone, if it exists, would live in a world of permanent twilight, with the star always on the horizon. The second challenge is stellar activity. Red dwarfs are not quiet stars. Young red dwarfs in particular are highly active, producing frequent and powerful flares that emit intense ultraviolet and X-ray radiation. These flares can be energetically comparable to the larger solar flares on our Sun, but because the planet must orbit so much closer to the star, the radiation dose is far more intense. A planet in the habitable zone of a young active red dwarf would experience radiation doses many orders of magnitude higher than Earth receives from solar flares. No one predicts that this is automatically fatal to life. Underground or ocean, dwelling life would be shielded from surface radiation. Life on Earth has been exposed to periodic radiation events from solar flares and nearby supernovae over billions of years and has survived. A thick atmosphere or a strong magnetic field could reduce the radiation reaching the surface. But the habitability environment around a young active red dwarf is significantly more hostile than Earth's, and the question of whether life can originate and sustain itself under those conditions is genuinely open. As red dwarfs age, they tend to settle down. The flare activity decreases over a few billion years as the star's magnetic field weakens. By the time a red dwarf is several billion years old, its flare activity may be comparable to or lower than the Sun's current activity level, making the stellar environment considerably more benign. But the first few billion years of a red dwarf's life, precisely the window during which life on Earth originated and diversified, could be deeply inhospitable for planets in the habitable zone. The third challenge is atmospheric loss. The close, inhabitable zones of red dwarfs expose planetary atmospheres to intense stellar wind and extreme ultraviolet irradiation that can gradually erode the atmosphere over geological timescales. The same Mervyn mission that measured atmospheric loss at Mars has given us a framework for understanding how stellar activity drives atmospheric erosion. A planet with a strong magnetic field, like Earth, is much better protected against this erosion than a planet without one. Red dwarf planets are expected to have a range of magnetic field strengths depending on their size, composition, and rotation rate. Observations are beginning to shed light on these questions. The TRAPPIST, one system, a red dwarf 40 light, years from Earth with 7 known Earth-sized planets, 3 of which are in or near the habitable zone, has been observed extensively by the Hubble Space Telescope and the James Webb Space Telescope. JWST has searched for atmospheres on TRAPPIST, 1b and TRAPPIST, 1c, the 2 innermost planets, finding no evidence for thick carbon dioxide atmospheres on either. This could mean the planets are airless, or it could mean their atmospheres are different from what was searched for. Analysis of TRAPPIST, 1e, TRAPPIST, 1f, and TRAPPIST, 1g, the planets in the more favourable part of the habitable zone, is ongoing. By the end of tonight, the red dwarf habitability question matters for tonight's story for a specific reason. If red dwarf planets can be habitable, then the stelliferous era of the universe, even in its long declining tail, offers habitable real estate for a far longer time than the brief window around Sun like stars. Sun, like stars, have sequence lifetimes of roughly 10 billion years. The most long-lived red dwarfs have sequence lifetimes of roughly 10 to 12 trillion years. If life can arise and sustain itself around red dwarfs, the window of cosmic habitability extends from a few tens of billions of years to roughly 10 trillion years. That is still a fraction of the universe's total future, still inside the stelliferous era, still closed long before the degenerate era begins. But it is roughly 1,000 times longer than the window that Sun, like stars, provide. Whether that matters for the frequency of life in the universe, and whether civilization of any kind can persist into the long red dwarf era, is one of the questions that makes the long-term future of the universe relevant to anything more than abstract theoretical cosmology. Before tonight's story moves entirely into the deep future, it is worth anchoring ourselves in the present and asking what the universe we actually observe tells us about where we are in the timeline. The current universe, as of 13.8 billion years after the Big Bang, is a specific snapshot of a much longer story, and reading that snapshot carefully reveals that the signs of cosmic decline are already visible. The cosmic star formation rate has been declining for roughly 10 billion years. We can measure this directly by observing galaxies at different redshifts, effectively looking back in time and counting the number of new stars forming at each epoch. The picture that emerges from these surveys, including the comprehensive measurements from the Hubble Space Telescope and the GALEX Ultraviolet Space Telescope, is clear. The universe converted gas into stars most efficiently around a redshift of roughly 1.5 to 2, corresponding to about 3 to 4 billion years after the Big Bang. Since then, the cosmic star formation rate has declined exponentially, falling by roughly a factor of 10 from its peak to the present day. The Milky Way illustrates this decline in microcosm. Our galaxy currently forms roughly 1 to 3 solar masses of new stars per year. This sounds like a lot until you consider that in the first few billion years of the Milky Way's existence, the rate may have been 10 to 50 times higher. The great molecular cloud complexes that produced the initial stellar populations of the bulge and the thick disk have largely been consumed. The gas that remains in the thin disk is still being converted to stars, but at a greatly reduced rate. The Milky Way is a mature declining star forming galaxy, not a young, vigorous one. No one expects this decline to be visible in the casual night sky. Human lifetimes are far too short to observe the change in star formation rate, and the existing stellar population is so numerous that the sky looks full of stars regardless. But on cosmological timescales, the decline is stark. In roughly 1 trillion years, the Milky Way, by then merged with Andromeda, and whatever other local group members get absorbed in the merger, will be an elliptical galaxy with a greatly reduced star formation rate, populated primarily by red dwarfs and stellar remnants. The observable universe today contains roughly 2 trillion galaxies across a volume of space about 93 billion light years in diameter. Most of those galaxies are already too far away for any future light from them to reach us, because dark energy is accelerating their recession. The galaxies that are within the cosmic event horizon today, those whose recession speed is less than the speed of light, will remain reachable, but their recession speed will increase over time as dark energy accelerates the expansion. Some galaxies that are currently within our event horizon will cross the horizon in the future and recede from us permanently. The local group, the cluster of perhaps 80 galaxies dominated by the Milky Way and Andromeda, is gravitationally bound. Dark energy is not powerful enough to separate gravitationally bound systems at the local scale. The local group will survive as a bound structure, even as all other galaxy groups recede beyond the event horizon. On a timescale of perhaps 100 billion to 1 trillion years, the local group will merge into a single, massive elliptical galaxy, isolated in an otherwise empty-appearing universe. By the end of tonight, we are at the very beginning of the long night. Not the night of a day, but the early moments of a cosmic day, night cycle that lasts incomprehensibly longer than anything that has come before. The 13.8 billion years of the universe's history so far, the entire period of stars and galaxies and planets and life, represents roughly 0.01% of the stelliferous era, and the stelliferous era itself, all 100 trillion years of it, represents a negligibly small fraction of the total future of the universe. We look up at a sky full of stars and we think we are surrounded by abundance, and we are. But abundance is not permanence. The abundance of the current universe is a temporary condition, a consequence of the universe's extraordinarily low initial entropy and the complex productive decline from that initial state toward maximum entropy. Every star we see is a machine that is spending down the universe's original capital of low entropy. When the capital is spent, the universe will no longer have enough organization to do anything interesting. That is not a reason for despair tonight. But it is a reason to look at the night sky with a slightly different kind of wonder. Not just wonder at the abundance of light and heat and chemical complexity that surrounds us, but wonder at the fact that we are here to see it, that we exist at a moment in the universe's history when it is still bright, still active, still capable of producing planets and chemistry and life. We are not at the beginning of everything, but we are in the beginning of what matters. Absolutely no one anticipates that the right response to tonight's story is sadness. The universe in 10 to the 100 years will be very different from the universe tonight, but the universe tonight is extraordinary. We are in the golden window. The question is not how to feel about that, but how to understand it. The mechanisms by which stars die are as varied as the stars themselves, and understanding the full spectrum from the most massive to the least massive stars gives the stelliferous era's end a more complete picture than the single story of the last red dwarf. The most massive stars, those with more than roughly 8 times the mass of our Sun, end their lives in core, collapse supernovae. These are among the most energetic events in the universe short of the Big Bang itself. When the iron core of a massive star, the endpoint of successive layers of nuclear burning, reaches a mass of roughly 1.4 times the Sun's mass, electron degeneracy pressure can no longer support it. The core collapses in less than a second, from a sphere roughly the size of Earth to one roughly 12 miles across. The collapse releases roughly 3 times 10 to the 46 joules of energy, the equivalent of the total light output of a typical galaxy over several billion years, almost all of it in the form of neutrinos. The outer layers of the star, no longer supported by the collapsed core, fall inward and then rebound explosively outward, producing the supernova that can briefly outshine an entire galaxy. The remnant of the core collapse is either a neutron star, if the core mass is below roughly 2 to 3 solar masses, or a black hole if the core is more massive. Neutron stars are supported against gravity by neutron degeneracy pressure and are approximately 12 to 15 miles in diameter, containing the mass of roughly 1.4 to 2 solar masses in that tiny volume. The density at the center of a neutron star is approximately 10 to the 17 kilograms per cubic meter, comparable to the density of an atomic nucleus. A cubic centimeter of neutron star material would weigh roughly 400 million tons on Earth's surface. Stars between roughly 8 solar masses and perhaps 25 solar masses produce supernovae and neutron stars. More massive stars may produce black holes directly, either as the remnant of a less energetic supernova or through a direct collapse without a bright supernova. The exact boundary between these fates depends on the initial mass, rotation rate, and chemical composition of the star, and it is an active area of stellar astrophysics research. Observations of supernovae from massive star populations have occasionally found stars that disappeared without a recorded supernova. Consistent with direct collapse to a black hole, stars with masses between roughly 0.5 and 8 solar masses, including our Sun, follow the path we described in tonight's earlier sections: red giant expansion, helium flash, asymptotic giant branch, planetary nebula, white dwarf. The planetary nebulae produced by these stars are some of the most beautiful objects in the night sky. The Cat's Eye Nebula, the Butterfly Nebula, the Owl Nebula. Each is a dying star's outer layers illuminated by its own hot remnant core. They are, in a physical sense, the light emitted by the process of dying, the last dramatic output of a star that has spent billions of years converting hydrogen to helium in relative quiet. Stars below roughly 0.5 solar masses down to the hydrogen burning threshold at about 7.5 to 8% of the Sun's mass are the red dwarfs. They skip the red giant phase and the planetary nebula. They do not synthesize carbon or oxygen in their cores in significant amounts. They live long and die quietly, contracting to a helium white dwarf directly from the main sequence over timescales of tens of trillions of years. Below the hydrogen, burning threshold are the brown dwarfs, objects that are too small to sustain hydrogen fusion, but that can briefly sustain deuterium fusion, a lower energy nuclear reaction involving heavy hydrogen, during their early lives. Brown dwarfs cool and dim continuously from their formation, spending their long lives as slowly fading infrared sources. They do not explode, they do not produce planetary nebulae. They simply cool over hundreds of billions to trillions of years toward the ambient temperature of the universe. No one predicts that the vast zoo of stellar deaths, from violent core collapse supernova to quiet white dwarf cooling, is easy to summarize in a single picture. But the important point for tonight's story is the end point. All of these processes lead to the same class of objects: white dwarfs, neutron stars, and black holes. These are the degenerate remnants that will populate the universe after the stelliferous era, slowly cooling and dispersing through the very long degenerate era. The heavy elements synthesized in stellar interiors and scattered by stellar deaths are the material substrate of everything we know about chemistry, biology, and life. The carbon in every living thing was made in the helium, burning cores of stars with masses a few times the Sun's mass, and then returned to the interstellar medium when those stars died. The oxygen was made in the same process. The iron in your blood was made in the cores of massive stars and returned to the interstellar medium in supernova explosions. The calcium in your bones, the silicon in the rocks beneath your feet, the gold and silver and uranium in Earth's crust. All of it was forged in stars that lived and died before the sun formed. The universe had to go through at least one, probably several generations of stellar birth, evolution, and death before the interstellar medium was enriched enough in heavy elements to allow the formation of rocky planets and life as we know it. The earlier stars, formed from almost pure hydrogen and helium, could not have hosted Earth, like planets, because there was no rock to make them from. The process of stellar nucleosynthesis and supernova enrichment that built up the heavy element content of the interstellar medium took billions of years, and it is still ongoing. Each generation of massive stars that lives and dies today is contributing to the heavy element content of the interstellar medium that will be available for the next generation of star and planet formation. In 100 trillion years, when the last red dwarf exhausts its hydrogen and the stelliferous era ends, the interstellar medium will be richer in heavy elements than it is today, enriched by an additional 86 trillion years of stellar nucleosynthesis. The white dwarfs of the degenerate era will be rich in carbon and oxygen, testaments to the billions of years of stellar processing that produced them. The neutron stars will contain the densest nucleosynthesis products, synthesized in the final seconds of massive star collapse under conditions of density and temperature that no other environment in the universe achieves. The heavy element legacy of the stelliferous era will be locked inside these remnants for the entire degenerate and black hole eras, until proton decay or quantum tunneling or Hawking radiation finally dissolves the last of it into radiation. The degenerate era begins when the last star dies. It ends when the last white dwarf goes dark. The last neutron star cools to the temperature of its environment, and the physical remnants of stellar evolution have either decayed or been absorbed by black holes. The time span of the degenerate era is staggering by any measure. It begins at roughly 100 trillion years and extends to roughly 10 to the power of 37 years, one followed by 37 zeros. That number is so much larger than 100 trillion that it barely makes sense to compare them. 100 trillion is 10 to the 14. The degenerate era ends at 10 to the 37. The degenerate era is 10 to the 23 times longer than the entire stelliferous era. In the degenerate era, the dominant objects in the universe will be white dwarfs, neutron stars, brown dwarfs, and black holes. There will be no stars fusing hydrogen. There will be no active galaxies, no supernovae, no star forming nebulae. The universe will have entered a kind of suspended state, its matter organized into dense cold remnants, slowly cooling, slowly dispersing, slowly interacting on gravitational timescales. White dwarfs are the most common remnant. Something like 97% of all stars that exist today will eventually end their lives as white dwarfs. The cooling rate of a white dwarf depends on its mass and initial temperature, but the general trajectory is clear. They cool from tens of thousands of degrees at formation to a few thousand degrees over billions of years, then to a few hundred degrees over trillions of years, then toward the temperature of their environment over times longer than the current age of the universe. A white dwarf that formed 10 billion years ago and has been cooling ever since is still hot enough to glow white or yellow. A white dwarf 10 trillion years from now will be a dim red ember. A white dwarf 100 trillion years from now will have cooled to temperatures barely above the background temperature of the universe. The background temperature of the universe is the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang that has been cooling as the universe expands. Currently about 2.725 Kelvin, roughly 460 degrees below 0 Fahrenheit, it will continue to cool as the universe expands, falling toward absolute zero asymptotically over trillions of years. The white dwarfs in the degenerate era will be cooling toward this slowly falling floor, their thermal energy leaking into a universe that is itself growing colder. No one expects the degenerate era to be eventful in the conventional sense. It is not an era of dramatic astronomical phenomena. It is an era of slow cooling, slow dispersion, slow gravitational interaction. But it is not entirely inert, and some of the processes that occur in the degenerate era are worth understanding, because they determine what kind of universe exists at its end. One of the most important processes in the degenerate era is the gravitational relaxation of stellar clusters and the eventual dissolution of galaxies. Gravitational systems made of many particles, including galaxies, are not in thermal equilibrium. They have internal energy distributions that are not stable over very long timescales. In a process called body relaxation, stars or stellar remnants in a gravitational system exchange energy through close gravitational encounters. Over time, this energy exchange leads to a tendency for some objects to accumulate more energy and escape from the system while others lose energy and sink toward the center. For a globular cluster, this process operates on timescales of billions to hundreds of billions of years. For a galaxy, it operates on much longer timescales, but still within the degenerate era. Estimates suggest that over timescales of 10 to the 19 to 10 to the 20 years, roughly 10 billion times the current age of the universe, gravitational evaporation will have dispersed most stellar remnants from even the largest galactic structures. The core of the former galaxy will have collapsed to a massive central black hole, surrounded by a sparse expanding cloud of ejected stellar remnants drifting outward into intergalactic space. The structure we call the Milky Way will not exist. Even the merged remnant of the Milky Way and Andromeda, the elliptical Milkdromeda galaxy, will eventually evaporate its stars in this way, with most of its stellar remnants scattered into intergalactic space, and only a massive central black hole remaining. Neutron stars, the remnants of massive star explosions, will also be present throughout the degenerate era. Neutron stars are supported against gravitational collapse by neutron degeneracy pressure, and they cool from initial temperatures of hundreds of billions of degrees at formation to near ambient temperatures over millions of years. A neutron star 100 trillion years old will be a dark, cold ball of neutrons approximately 12 miles in diameter, detectable only by its gravitational field. Many neutron stars will be isolated in intergalactic space by the time the degenerate era is well underway, ejected from their parent galaxies by the gravitational evaporation process over the preceding trillions of years. Brown dwarfs, objects that are larger than planets, but not massive enough to ignite hydrogen fusion, will also drift through the degenerate era. A brown dwarf with perhaps 80 times the mass of Jupiter, just below the threshold for hydrogen fusion, formed during the stelliferous era, will spend the entire degenerate era cooling and contracting, never undergoing nuclear reactions, but too dense to be classified as a planet. By the end of the degenerate era, it will be a cold, dark, supported ball of degenerate matter, essentially a large white dwarf composed primarily of hydrogen and helium rather than carbon and oxygen. By the end of tonight, the degenerate era is not a dead universe. It is a dark and cooling universe full of material, full of structure, full of the remnants of the stelliferous era. But it is one in which light is produced only by the slow thermal emission of cooling objects, one in which the timescales for any significant event are so long that even the 13.8 billion year history of the universe we know is a brief moment by comparison. And at the end of the degenerate era, a new and more fundamental process intervenes. Dark matter complicates the picture of the universe's long-term future in ways that are difficult to quantify, precisely because we do not know what dark matter is. We know it exists. We know it accounts for roughly 27% of the total energy content of the universe, compared to roughly 5% for ordinary baryonic matter and roughly 68% for dark energy. We know it clumps gravitationally and is responsible for the large-scale structure of galaxies and galaxy clusters. What we do not know is what particle or particles constitute it, how it interacts, and whether it is stable or whether it decays over sufficiently long timescales. The leading candidates for dark matter in the current literature are weakly interacting massive particles, WIMPs, which would be roughly 10 to 1,000 times the mass of a proton and interact with ordinary matter only through the weak nuclear force and gravity. WIMPs would have been produced in large numbers in the hot early universe and would have survived to today because their interaction cross-section is too low for them to annihilate efficiently. If WIMPs are the dark matter, they are present everywhere in the galaxy today, including in the solar system, in your body as you listen to this. Several thousand WIMP particles may pass through each square inch of your body every second. No one expects WIMPs to be directly dangerous or detectable without purpose, built instruments. Their interaction probability is extremely low. Multiple underground detectors, including Xenon 1T, ELUX, Zeppelin and Pandex 4T, have searched for WIMP interactions with ordinary matter at extraordinary sensitivity without finding a definitive detection. This does not rule out WIMPs, but it has constrained their possible masses and interaction strength significantly. For the long-term future of the universe, what matters is not whether we can detect dark matter today, but whether dark matter particles decay on cosmological timescales. If WIMPs are absolutely stable, they persist throughout the stelliferous era, the degenerate era, the black hole era, and the dark era. In the dark era, dark matter particles would be the most numerous massive particles in the universe, drifting apart in the expanding void. They would not clump into structures, because the gravitational potential wells needed to hold them together, galaxy clusters and galactic halos, would long since have evaporated through the processes that disperse baryonic matter. The dark matter particles would simply drift, slowly, in an increasingly empty universe. If WIMPs can annihilate with WIMPs, even at very low rates, they will gradually reduce in number over astronomical timescales. In regions of higher dark matter density, such as the cores of surviving galactic remnants, WIMP annihilation would proceed faster. The energy produced by WIMP annihilation, which typically produces gamma rays and standard model particles, would provide a tiny but persistent energy source in the degenerate era. Estimates suggest that in halos of concentrated dark matter, WIMP annihilation could provide more luminosity than proton decay for a period in the early degenerate era, if proton decay occurs on the timescales predicted by simple grand unified theories. The alternative dark matter candidates include axions, much lighter hypothetical particles that were proposed to solve a different problem in particle physics, the strong CP problem. Axions, if they exist, would be extraordinarily light, with masses perhaps 10 to the -5 electron volts, far less than even a neutrino. They interact with photons in the presence of a magnetic field, which is the basis for axion detection experiments like ADMX. Their cosmological fate depends on their specific properties. Some axion models predict that axions could undergo Bose-Einstein condensation on long timescales, forming strange quantum states of matter in the cold universe. Primordial black holes are another dark matter candidate that have received renewed attention in recent years. If a significant fraction of dark matter is composed of black holes that formed in the very early universe, before any stars existed, then the story of the dark matter's evolution in the far future is simply the Hawking evaporation story, applied to a vast population of primordial black holes. Depending on their mass distribution, primordial black hole dark matter would add a significant population of objects to the black hole era, all gradually evaporating through Hawking radiation. Dark matter's role in the universe's long-term future is uncertain in ways that reflect our fundamental ignorance about its nature. What is certain is that dark matter, whatever it is, constitutes the majority of the matter in the universe today, and plays a dominant role in the gravitational dynamics that will govern the universe's structure through the entire stelliferous era and into the degenerate era. Understanding what it is and how it behaves over these timescales is one of the central outstanding problems in cosmology, and its resolution will significantly shape our picture of the universe's long-term future. Entropy is the concept at the centre of tonight's story, and it is worth spending time on it carefully, because it is one of those ideas that sounds simple and turns out to have layers that keep unfolding the longer you examine it. The standard definition is that entropy is a measure of disorder. A neat organised room has low entropy. The same room after a party has high entropy. Entropy increases over time because there are far more ways for a system to be disordered than ordered. That definition is not wrong, but it is incomplete. A more precise statement is that entropy is a measure of the number of microscopic configurations that correspond to a given macroscopic state. A low entropy state is one where relatively few microscopic configurations could produce the observed macroscopic state. A high entropy state is one where many microscopic configurations could produce the observed macroscopic state. Because there are more high entropy configurations than low entropy configurations, a system left to evolve randomly will almost certainly move toward higher entropy states. The second law of thermodynamics is the statement that the total entropy of a closed system can never decrease over time. In practice, for the universe as a whole, which is the ultimate closed system, entropy has been increasing continuously since the Big Bang and will continue to increase until the universe reaches thermodynamic equilibrium, the state of maximum entropy. That state is what tonight's episode is calling the dark era or heat death. No one expects the Big Bang to have been a high entropy state, even though it was hot and dense. This is counterintuitive. We tend to associate high temperature with disorder and low temperature with order, but the entropy of the early universe was actually very low, not because it was cold, but because the matter was distributed almost perfectly uniformly, with only tiny quantum fluctuations that would eventually seed the large scale structure of galaxies. A perfectly uniform distribution of matter is actually a low entropy state from the perspective of gravity. Gravity prefers to cluster matter together, and a uniform distribution represents an untapped potential for gravitational organization. The low entropy of the early universe is why stars and galaxies could form. As the universe expanded and cooled, gravity caused small overdensities to collapse into larger and larger structures, molecular clouds, then stars, then galaxies. Each time matter fell into a gravitational potential well, it released gravitational potential energy as heat, radiation, and kinetic energy, increasing entropy. The formation of stars is an entropy, increasing process. The fusion of hydrogen into helium inside stars is an entropy, increasing process. The supernova explosions that end massive stars' lives are entropy, increasing processes. Every event in the history of the cosmos, every star birth, every galaxy merger, every black hole accretion event has pushed the universe toward higher entropy. The low entropy initial condition of the universe is one of the deepest unresolved questions in physics. Why did the universe begin in such an extraordinary low entropy state? The answer is not obvious. Random initial conditions would almost certainly produce a much higher entropy starting point. The fact that the universe started in a low entropy state and has been increasing in entropy since then is what gives the arrow of time its direction. We experience time as flowing from past to future, from cause to effect, from before to after, because entropy increases in that direction. A universe in thermal equilibrium at maximum entropy has no arrow of time because there is no direction in which change preferentially occurs. In the dark era, the universe will be close enough to maximum entropy that the arrow of time will effectively have disappeared. Events will still occur in the sense that quantum fluctuations will still happen and particles will still interact. But there will be no preferred direction of change, no tendency for complexity to emerge, no process that distinguishes the future from the past. Time will still pass, in the sense that the parameter in the equations of physics will continue to increase. But there will be nothing to measure it by. Absolutely no one anticipates that this is comforting. The arrow of time is so deeply built into our experience of existence that a universe without it is almost impossible to imagine. But it is the logical consequence of entropy maximization, and it is what the physics says about the far future of the universe. The dark era is not just dark, it is timeless, in the sense that matters most. There is nothing in it that could serve as a clock. The relationship between entropy and information is also relevant tonight. Information, in the technical sense used by Claude Shannon in his 1948 paper Founding Information Theory, is quantitatively related to entropy. A message is informative to the extent that it reduces our uncertainty about which of many possible states actually obtained. A high entropy system is one where many microscopic configurations could correspond to the same macroscopic description, meaning that precise knowledge of the macroscopic state provides relatively little information about the microscopic state. Entropy and information are inversely related. Low entropy means high information content. High entropy means low information content. In the dark era, the total entropy of the universe is at its maximum, which means the information content of the universe's state, the amount of information needed to specify the exact microscopic configuration, is also at its maximum, but the information is not accessible. It is diluted across an enormous, low temperature background of radiation and particles with no organized structure to make it readable. The universe in the dark era contains, in some theoretical sense, all the information about everything that ever happened, encoded in the precise positions and momentaire of its photons and leptons. But it is encoded so thoroughly, scrambled so completely by entropy increase, that no physical process could recover it. Entropy is not an abstract concept. It is the force that drives the universe from the bright, complex, brief, stelliferous era into the long, dark, structureless dark era. It is why the window is shorter than you think. Not because the universe ends soon, but because order ends soon, relative to the universe's total future. Proton decay is the process that may ultimately end the degenerate era. If protons are not stable, if they eventually decay into lighter particles over sufficiently long timescales, then the white dwarfs, neutron stars and brown dwarfs of the degenerate era are not permanent. They are temporary structures that will dissolve into a fog of lighter particles and radiation as their constituent protons disappear one by one. The question of whether protons decay is one of the most important open questions in particle physics. Within the standard model of particle physics, protons are absolutely stable. They cannot decay because there is no lighter baryon for them to decay into, and baryon number conservation prevents the transition. But the standard model is not the final word on particle physics. It is an incomplete theory, known to break down at very high energies and failing to explain several observed phenomena including the matter-antimatter asymmetry of the universe. Many extensions of the standard model, particularly the grand unified theories that attempt to merge the strong, weak and electromagnetic forces into a single framework, predict that protons are not absolutely stable, but instead decay on extremely long timescales. The most commonly discussed proton decay mode in grand unified theories is the decay of a proton into a positive pion and a positron. This is the mode that current experiments search for. The current best experimental limit on the proton lifetime for this decay mode, from the Super Kamiokande detector in Japan, exceeds 10 to the 34 years. The universe is currently 13.8 billion years old, which is roughly 1.38 times 10 to the 10. The experimental lower bound on proton lifetime is 10 to the 34, which is roughly 10 trillion times the current age of the universe. Proton decay, if it happens at all, happens extraordinarily slowly. But for cosmological purposes on the timescales of the degenerate era, An extraordinarily long proton lifetime is not the same as no proton decay. If the proton lifetime is 10 to the 34 years, then in a sample of 10 to the 34 protons, roughly 1 proton will decay every year. The human body contains roughly 7 times 10 to the 27 protons. If protons have a lifetime of 10 to the 34 years, then 1 proton in a human body would decay every few million years, a rate that is undetectable by any current instrument. But over 10 to the 37 years, every proton in a white dwarf would have decayed many times over if the proton lifetime is in the range predicted by simple grand unified theories. No one predicts this with certainty, because proton decay has not been observed. But the theoretical case for proton decay at some level is strong, and the cosmological consequences are profound. If protons do decay, even on timescales of 10 to the 34 to 10 to the 40 years, then the end of the degenerate era is not a slow cooling into permanent darkness, it is dissolution. The matter of the degenerate era, all those white dwarfs and neutron stars and cold brown dwarfs, does not persist forever. It evaporates, proton by proton, into radiation and leptons. The specific products of proton decay depend on the exact mechanism and energy. In the positron pion decay channel, each decaying proton produces a positron and a neutral pion. The neutral pion almost immediately decays into 2 gamma ray photons. The positron will eventually encounter an electron and annihilate into 2 more gamma ray photons. So each decaying proton produces roughly 4 gamma ray photons and no baryons. The matter content of the degenerate era objects is converted, proton by proton and neutron by neutron, into radiation. The rate of energy production from proton decay in a white dwarf is tiny. A white dwarf with roughly half the mass of the Sun contains approximately 10 to the 57 protons and neutrons. If the proton lifetime is 10 to the 34 years, then roughly 10 to the 23 decays occur per year in a white dwarf, each producing energy equivalent to the proton's mass, energy of about 938 MeV. This works out to a steady power output of perhaps 10 to the minus 20 watts, approximately 0 by any conventional standard. A human hair falling on a table delivers more energy. But it is not 0, and it is constant, and over 10 to the 37 years it is sufficient to dissolve the entire white dwarf. The process is not a sudden event. A white dwarf, undergoing proton decay, does not explode or collapse. Its structure slowly loses mass over timescales of trillions of times the current age of the universe. As mass is lost through decay, the object contracts slightly in response to reduced internal pressure. The thermal energy deposited by the decay reactions briefly warms the object above the ambient temperature of the universe, giving it a very faint thermal glow. In a sense, the white dwarf in the late degenerate era is powered by proton decay radiation in the same way the main, sequence Sun is powered by nuclear fusion. Both are converting mass to energy and radiating it into space. The timescales and power levels are incomparably different, but the physics is analogous. Absolutely no one anticipates observing proton decay directly, not in any astrophysical context. The rates are far too low and the distances far too large. But the theoretical framework predicts it, and if it occurs on the timescale suggested by grand unified theories, it will be the primary mechanism by which ordinary matter in the degenerate era is converted into radiation. By the end of the degenerate era, if proton decay operates, there will be essentially no ordinary baryonic matter left in the universe. The white dwarfs and neutron stars and brown dwarfs will be gone. The universe will consist primarily of black holes and the radiation and leptons produced by proton decay. If proton decay does not operate on these timescales, if protons are truly stable or have lifetimes much longer than grand unified theories suggest, then a different process takes over at extremely long timescales. Quantum mechanical tunneling will slowly cause the nuclei in white dwarfs and neutron stars to reorganize into the most energetically favorable nuclear configuration. Iron, 56, the most tightly bound nucleus. Over timescales of roughly 10 to the 1500 years, a white dwarf composed of carbon and oxygen will slowly, atom by atom, quantum tunnel toward an iron configuration. This is such an extreme timescale that it is difficult to even conceive of it in comparison to any other numbers in this story, but it is physically predicted. The iron star that results would eventually quantum tunnel into a black hole, over timescales measured in 10 to the 76 years. These are not numbers that have any intuitive meaning. They are simply the physical consequences of quantum mechanics operating over arbitrarily long timescales. One detail from the degenerate era deserves a moment of its own: the iron star. If proton decay does not operate, if ordinary matter is genuinely stable on timescales far longer than grand unified theories suggest, then the white dwarfs and neutron stars of the degenerate era have an alternative fate. At temperatures close to absolute zero, quantum tunneling allows nuclei to rearrange themselves without requiring the thermal activation energy that classical physics would demand. The iron nucleus, iron 56, is the most tightly bound nucleus in the periodic table. Given an arbitrarily long time, any nucleus in a white dwarf, whether carbon or oxygen or the helium ash of a red dwarf, will eventually quantum tunnel through the energy barrier separating it from the iron 56 ground state. This process is excruciatingly slow. The timescale for a single carbon nucleus to tunnel to iron is estimated at roughly 10 to the 1500 years, which makes the black hole era look fleeting. But on timescales of 10 to the 1500 years, every carbon nucleus in every white dwarf in the former universe will have tunneled. The white dwarf will have transformed, atom by atom over inconceivable timescales, into a sphere of iron. Not hot iron, not liquid iron, but cold, degenerate iron, a quantum mechanical structure held up by electron degeneracy pressure at near absolute zero temperature. The iron star, as it is sometimes called, is the ultimate fate of ordinary matter if protons are truly stable. No one expects this to be observable, even in principle, but it is what the physics says happens if you wait long enough. The iron star will eventually, through a similar quantum tunneling process operating on an even longer timescale, collapse into a black hole, and the black hole will evaporate through Hawking radiation, and the universe will be left with nothing but photons and leptons, regardless of whether proton decay operates. The endpoint is the same, the path is different. The timescales are so different that one makes the other look like an instant. But both roads lead to the dark era. When the degenerate era ends, whether through proton decay, quantum tunneling, or some other process we do not yet fully understand, what remains are black holes. Not because black holes are immune to these processes, but because they are immune to proton decay. Black holes do not contain protons in any conventional sense. They are regions of space-time where the curvature has become so extreme that nothing, not matter, not radiation, not information, can escape from within the event horizon. There are no protons inside a black hole to decay. There is no ordinary matter inside a black hole to tunnel into iron. A black hole is not a ball of neutrons or carbon. It is a singularity, a point where the known laws of physics break down, surrounded by an event horizon. But black holes do not live forever. This was the profound discovery that Stephen Hawking made in 1974, connecting general relativity with quantum mechanics in a calculation that shocked the physics community. Quantum mechanics predicts that the vacuum of empty space is not truly empty. It is filled with virtual particle pairs, particle and antiparticle, appearing together from the vacuum and annihilating each other again on timescales too short to violate energy conservation. This quantum fluctuation process occurs everywhere in space at all times. Near the event horizon of a black hole, Hawking showed, a peculiar thing can happen. A virtual pair can appear straddling the event horizon, with one particle inside and one outside. The particle inside falls inward and is absorbed by the singularity. The particle outside, denied its annihilation partner, becomes real and escapes into space. From outside the black hole, it looks as if the black hole is emitting radiation at a temperature that depends on the black hole's mass. This radiation is called Hawking radiation. It carries energy away from the black hole. Since the energy has to come from somewhere, and the black hole is the only thing present, the energy comes from the black hole's mass. The black hole slowly loses mass, radiating energy into space as Hawking radiation, until it has lost all of its mass and disappears in a final burst of high-energy particles and radiation. The rate of Hawking radiation is inversely proportional to the square of the black hole's mass. A black hole with the mass of a mountain would evaporate in fractions of a second. A black hole with the mass of our Sun would take roughly 10 to the 67 years to evaporate. A supermassive black hole, like the 4 million solar mass object at the centre of the Milky Way, would take roughly 10 to the 83 years. The supermassive black holes at the centres of the largest galaxies, some of which contain billions of solar masses, would take up to roughly 10 to the 100 years, sometimes called a Google years, to fully evaporate. No one expects the Hawking radiation from current stellar mass or supermassive black holes to be detectable. The temperature of the Hawking radiation from a stellar mass black hole is on the order of 10 to the negative 8 Kelvin, which is 100 millionths of a degree above absolute zero, far colder than the cosmic microwave background. The radiation is so faint and so cold that it is completely overwhelmed by everything else in the universe. But on the timescales of the black hole era, all other sources of radiation will have faded. The cosmic microwave background will have been redshifted to temperatures far lower than the initial Hawking temperature of the black holes, and the black holes will have lost enough mass through evaporation that their temperatures will have risen, slowly at first and then faster, as the mass decreases and the temperature increases. The black hole era is the era from the end of the degenerate era, roughly 10 to the 37 to 10 to the 40 years, to the evaporation of the last supermassive black hole, roughly 10 to the 100 years. During this entire era, the dominant energy source in the universe will be Hawking radiation from black holes of various masses, growing hotter and more luminous as each black hole loses mass and approaches its final evaporation burst. The universe in the black hole era is not entirely dark. It is illuminated by the very faint thermal emission of black holes in their long Hawking evaporation, punctuated occasionally by the dramatic burst of high energy radiation from a black hole reaching its final stages of evaporation. A stellar mass black hole in its final days emits a burst of energy equivalent to many nuclear warheads, concentrated in an extremely short time. A supermassive black hole in its final burst emits energy equivalent to billions of nuclear warheads simultaneously. In a universe with no stars, no galaxies, no other significant energy sources, these evaporation bursts will be the last fireworks. By the end of tonight, the black hole era is the penultimate chapter of the universe's story. It is an almost inconceivably long chapter. The entire stelliferous era, 100 trillion years, is 10 to the 14. The black hole era extends to 10 to the 100. The ratio between the stelliferous era and the black hole era is 10 to the 86, a number so large that it defies any analogy. The black hole era is to the stelliferous era what the total age of the universe is to the smallest unit of time in quantum mechanics, the Planck time, and then repeated several more times. In the black hole era, the brief flash of stars and life and planetary systems that define the stelliferous era is not just old history. It is so ancient that no physical record of it survives. The heavy elements produced in stellar nucleosynthesis have long since been absorbed into black holes, converted to Hawking radiation, or dispersed so thinly through the expanding universe that no concentration exists anywhere. The information about the stelliferous era is not gone, according to current theoretical understanding, because quantum mechanics requires information to be conserved, but it is so thoroughly scrambled and diluted that it is effectively irretrievable by any physical process. The last event of the black hole era is the evaporation of the largest supermassive black holes. Some galaxies today contain black holes billions of times the mass of our Sun. Those black holes will be the last objects in the universe with significant mass concentrations. As they evaporate through Hawking radiation over timescales approaching 10 to the 100 years, they will glow with increasing temperature and intensity, producing a final burst of energetic radiation as each one disappears. The very last supermassive black hole to evaporate will produce what amounts to the last significant event in the history of matter, as we understand it. After that, the universe will have entered the dark era. The supermassive black holes at the centres of galaxies are among the most massive objects in the universe, and they will be among the last. Understanding what they are, how they formed, and how they will eventually disappear is central to tonight's story of the black hole era. Supermassive black holes have masses ranging from millions to billions of times the mass of the Sun. The black hole at the centre of the Milky Way, Sagittarius A, has a mass of roughly 4 million solar masses and occupies a volume smaller than the radius of Mercury's orbit around the Sun. The Event Horizon Telescope collaboration produced the first direct image of Sagittarius A in 2022, resolving the shadow of the black hole's event horizon against the glowing ring of hot gas surrounding it. The image, released after years of data analysis, confirmed the presence of a compact object with the properties predicted for a supermassive black hole, validating decades of indirect evidence. The most massive known supermassive black holes, including the black hole at the centre of the galaxy TON 618 with an estimated mass of 66 billion solar masses, are embedded in the most luminous galaxies in the early universe. How black holes of such masses formed is still debated. The leading hypotheses involve the mergers of many smaller black holes over cosmic time, combined with periods of rapid accretion, during which the black hole gains mass extremely quickly when it's surrounded by abundant infalling gas. The early universe, dense with gas and characterized by rapidly merging galaxy structures, provided ideal conditions for both processes. No one predicts that supermassive black holes are growing significantly today. The current universe is past its peak of quasar activity, when supermassive black holes were accreting gas at high rates and shining as the most luminous persistent objects in the cosmos. Today, most supermassive black holes are in quiescent states, accreting little material and emitting little radiation. Sagittarius AI is a comparatively quiet black hole by the standards of the early universe quasars, flaring occasionally when it accretes infalling material but not continuously active. In the degenerate and black hole eras, supermassive black holes will dominate the gravitational landscape of their former host galaxies. As the stars and stellar remnants of the galactic environment are gradually evaporated through gravitational relaxation, some fraction of them will fall into the central black hole. The mass of the central supermassive black hole will grow modestly during the degenerate era through such accretion, but the rate will be extremely low, limited by the supply of infalling material in an increasingly sparse environment. The eventual fate of supermassive black holes is Hawking evaporation. As we discussed, a supermassive black hole with the mass of TON 618, 66 billion solar masses, will take approximately 10 to the 100 years to evaporate. This timescale is so long that it is effectively the definition of the black hole era's duration. All ordinary matter in the universe will be gone long before the most massive black holes finish evaporating. The final evaporation of a supermassive black hole is not a gentle fading. As a black hole loses mass through Hawking radiation, its temperature rises and the rate of energy emission increases. This creates a positive feedback loop. As the black hole gets smaller, it gets hotter, it radiates faster, it gets smaller faster, it gets hotter faster. The final stages of evaporation occur on increasingly short timescales. A black hole that has been slowly evaporating for nearly 10 to the 100 years will, in its final milliseconds, release as much energy as the Sun radiates in its entire main, sequence lifetime, compressed into a burst of high-energy particles and gamma radiation. In the context of the Dark Era's extreme emptiness, that burst will be the last significant event in the universe's history before the final quiet. Absolutely no one anticipates that these bursts will be observed. By the time supermassive black holes are in their final stages of evaporation, no material structures exist that could serve as detectors. But the burst is real, predicted by the same physics that Hawking derived in 1974, and it is the universe's final dramatic act. By the end of tonight, supermassive black holes serve as a kind of anchor for tonight's story. They formed early in the universe's history and will persist longest. They bridge the stelliferous era, where they grew through accretion during the quasar epoch, through the degenerate era, where they slowly accumulate the last in falling remnants, through the black hole era, where they dominate as the universe's last massive structures, to their eventual final evaporation. They are the last chapter in the story of matter, and their final burst will be the last sentence. The question of what tonight's story means for civilization, if civilization continues to exist on timescales much longer than our current existence, is one that has been explored by a small but serious community of physicists and futurists. It is speculative, necessarily so, but grounded in the same physical principles we have been discussing. If the universe has a long future and physics places constraints on what kinds of structures can exist in that future, then any sufficiently advanced civilization would need to understand those constraints and adapt to them. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy usage. A Type 1 civilization controls the entire energy output of its home planet. A Type 2 civilization controls the energy output of its home star. A Type 3 civilization controls the energy output of its entire galaxy. We are currently somewhere below Type 1, capable of using only a fraction of Earth's received solar energy. The scale is a rough guide to the energy resources a civilization has access to, and the kinds of feats it could in principle accomplish. No one predicts that any civilization today is Type 2 or Type 3, but the framework is useful for thinking about how civilizations might navigate the long-term future. A Type 2 civilization, one that can fully exploit the energy output of its star, could in principle migrate from star to star as its home star ages, moving to younger, longer-lived stars to extend its energy supply. Red dwarfs, with their trillion-year lifetimes, would be particularly attractive targets for any civilization thinking on billion-year timescales. Freeman Dyson, the physicist who proposed the theoretical concept of a Dyson sphere, also wrote extensively about the long-term prospects for life and intelligence in the universe. In a 1979 paper, Dyson proposed that life and intelligence could in principle survive indefinitely in the universe, even as it cooled toward a maximum entropy, by adapting to lower and lower temperatures and slower rates of information processing. The key insight is that thinking, in an abstract physical sense, does not require any particular temperature. It requires a system that can process information, store it, and retrieve it. As long as there is a temperature difference somewhere in the universe, energy can be extracted to power computation and information processing. Dyson's argument was that an intelligence powered by the diminishing energy resources of the cooling universe could extend its total subjective experience indefinitely, even if the objective time between thoughts grew longer and longer. This is the concept of subjective versus objective time, an intelligence running slower and slower, processing thoughts over longer and longer intervals of objective time, might still experience an infinite subjective duration. The universe's arrow of time would stretch the gaps between thoughts, but would not stop thoughts from occurring. The physicists Lawrence Krauss and others have pointed out a fundamental problem with Dyson's scenario: dark energy. In a universe dominated by a cosmological constant, the accelerating expansion produces a de Sitter horizon, a finite region beyond which nothing can be received. A civilization confined to the causal patch of de Sitter space has access to a finite declining pool of energy. The de Sitter temperature, which places a lower bound on the temperature of any physical system in the universe, is extremely small, roughly 10 to the minus 30 Kelvin, but it is not zero. Any physical system operating at temperatures below the de Sitter temperature would violate thermodynamics by extracting heat from a cooler reservoir. This places a finite limit on the total computation that can ever be performed in a de Sitter universe. Absolutely no one anticipates this to be practically relevant to any civilization that exists today or in the near stellar future. The de Sitter temperature limit becomes relevant only on timescales approaching the dark era, when all other energy sources have been exhausted. But it does suggest that Dyson's vision of an eternally persisting intelligence is blocked by dark energy. If dark energy is truly a cosmological constant, then the total subjective experience of any physical intelligence in the universe is finite, bounded by the finite total computation allowed by the de Sitter energy budget. This is the deeper answer to tonight's question. The amount of time the universe has left is shorter than you think, not only for structures like stars and planets, but potentially for consciousness itself. If intelligence requires energy to maintain its processes, and if the available energy in the universe is ultimately limited by the de Sitter bound, then not only does the window for planetary life close at the end of the stelliferous era, but the window for any kind of organized information processing may close at some finite time in the black hole era, long before the last Hawking burst fades. This is one of the genuinely profound implications of dark energy that is not often discussed in popular accounts. We tend to think of dark energy as a mysterious driver of the universe's expansion, something to marvel at for its strangeness and its implications for the universe's geometry. But its thermodynamic implications, specifically the fact that it imposes a finite de Sitter temperature floor on the universe's cooling, may ultimately limit the total cognitive capacity of the universe. The universe is, in this sense, not just a place that will eventually go dark. It is a computation with a finite budget, already well underway. The budget is large. The total computation available in a de Sitter universe with our cosmological constant is estimated at around 10 to the 120 operations, an almost incomprehensible number, but a finite one. For comparison, the human brain performs roughly 10 to the 17 operations per second, or about 3 times 10 to the 24 operations per year. At current rates, the human brain would exhaust the universe's remaining computational budget in roughly 10 to the 95 years, well before the end of the black hole era. But if intelligence becomes more energy, efficient over time, as Dyson's framework suggests, the budget could last much longer. No one expects this calculation to be practically useful, but it illustrates the point tonight's story is making in a very concrete way. The universe is a bounded resource in every sense that matters. The time it offers for stars is bounded. The time it offers for life is bounded. The time it offers for thought may be bounded. And by cosmic standards, that boundary is not infinitely far away. Tonight, deep in the dark era, something strange happens. Or rather, something strange might happen, given enough time. The concept is called Poincare recurrence, and it is one of the more unsettling implications of classical statistical mechanics applied to a finite physical system. The Poincare recurrence theorem, proven by the mathematician Henri Poincare in 1890, states that any finite dynamical system in equilibrium will, given enough time, return arbitrarily close to any previous state. The intuition is that the number of possible configurations of a finite system is large but finite, and if the system evolves long enough, it must revisit configurations it has been in before. For a simple system like a gas of particles in a box, the Poincare recurrence time depends on the number of particles and the precision with which the recurrence must occur. For a box of gas at room temperature, the recurrence time is so long that it makes the black hole era look brief. For the observable universe, the Poincare recurrence time has been estimated at approximately 10 to the 10 to the 10 to the 10 to the 10, a power tower of exponents that is essentially impossible to write out in decimal. This number is so incomprehensibly large that it exceeds the Googleplex, which is already 10 to the power of a Google, itself 10 to the 100. In practice, Poincare recurrence for a system as large and complex as the universe is purely theoretical. No physical process could survive or record information across such timescales. But the theorem says that if the universe is truly eternal and truly has a finite number of accessible states, it will eventually revisit states similar to the current one. This is where the Boltzmann brain comes in. The physicist Ludwig Boltzmann, grappling with the question of why the universe is in the low, entropy, highly ordered state we observe, suggested a provocative possible answer. Perhaps the observed universe is itself a statistical fluctuation from a much longer equilibrium. Given infinite time, a universe in thermal equilibrium will occasionally fluctuate into lower entropy states. Most such fluctuations would produce only small local ordering. Occasionally a fluctuation might produce something much more elaborate, including, in principle, a complete human brain with all its memories and perceptions intact, having materialized spontaneously from a soup of thermal radiation. No one expects a Boltzmann brain to be a common occurrence. The probability is extraordinarily small, but the Boltzmann brain argument, taken seriously, implies that in an eternal universe, spontaneous fluctuations that produce observers are more common than the ordered processes that produce the observable universe as we know it. This leads to the troubling conclusion that if you exist, it is statistically far more likely that you are a Boltzmann brain that materialized moments ago with false memories than that you are an evolved biological organism in a 13.8 billion year old universe with a real history. Most physicists do not take the Boltzmann brain scenario seriously as a description of our actual situation, for reasons both philosophical and physical. Philosophically, the argument assumes that the relevant probability measure over possible observers is the one that maximizes the frequency of observer, like fluctuations over infinite time, which is a non-trivial assumption. Physically, de Sitter space, the space-time geometry driven by dark energy, has properties that may limit the applicability of Poincare recurrence in ways that prevent Boltzmann brains from occurring in our cosmological future. But the Boltzmann brain problem illustrates something important about the dark era. The behavior of a de Sitter universe over extremely long timescales is not well understood. We know the physics of de Sitter space in the regime we can calculate. We do not know whether de Sitter space is truly eternal, whether it has quantum instabilities that would eventually cause it to transition to a different space-time geometry, or whether the quantum vacuum that generates de Sitter expansion is stable against large fluctuations over timescales of 10 to the 100 or more years. One possibility that has received attention in recent theoretical physics is the false vacuum scenario, the quantum field theory that describes the vacuum of space, including the Higgs field, may not be in its true minimum energy state. The current vacuum might be a local minimum, a metastable state that appears stable at low temperatures, but could in principle tunnel quantum mechanically to a lower energy true vacuum. If that tunneling occurred, it would produce a bubble of true vacuum expanding at the speed of light, transforming the physical laws within it as it went. The transformation would be fatal to any structures that the bubble encountered, and the bubble would spread without any warning at the speed of light, leaving nothing inside it. Calculations of the stability of the Higgs vacuum, using the measured values of the Higgs boson mass and top quark mass from the Large Hadron Collider, suggest that the current vacuum is on the boundary between stable and metastable, a region sometimes called the critical stability zone. The uncertainties in the calculation are large enough that we cannot definitively say whether the vacuum is stable, metastable, or unstable. If metastable, The lifetime of the current vacuum could be anywhere from far longer than the universe's current age to shorter than 10 to the 100 years. If a vacuum decay bubble has already nucleated somewhere in the observable universe, we would have no warning before it arrived. Absolutely no one anticipates a vacuum decay event in the near future, and current estimates suggest the probability is cosmically small on human timescales. But it is one of the genuinely physical uncertainties about the universe's long-term future that is not often included in popular accounts of cosmic timelines. The neat sequence of eras we have described, stelliferous to degenerate to black hole to dark, assumes that the physical laws remain constant and the quantum vacuum remains stable throughout. That assumption may or may not be warranted. Tonight, the Poincare recurrence and false vacuum scenarios are not included to frighten or to suggest that the universe is fragile. They are included because the physics of the far future is genuinely uncertain, and intellectual honesty requires acknowledging where the extrapolations of known physics become speculative. The broad outline of the timeline we have described is robust. The universe will get darker, colder, and less structured over time. The exact sequence and the behavior of the universe at truly extreme timescales remain open questions at the frontier of theoretical cosmology. Tonight, it helps to put all of these timescales side by side, because the numbers are so extreme that they resist intuition without comparison. Let us build a scale. The current age of the universe is 13.8 billion years. If we compress the entire stelliferous era, all 100 trillion years of it, into a single calendar year, then the current moment in cosmic history is the early morning of January 1st. The Sun will not begin its red giant phase until sometime in late October. The last red dwarf will burn out on December 31st at approximately 11:59 p.m. The entire history of the universe from the Big Bang to the present day, all 13.8 billion years of it, would occupy roughly the first hour and 20 minutes of January 1st. Now extend the scale to the degenerate era. If the stelliferous era is 1 year, the degenerate era is 100 million years. 100 million years, in the same units where the entire age of stars is a single calendar year. The cooling white dwarfs and slow, gravitational evaporation of galactic remnants unfold over a time span that makes the entire stelliferous era look like a moment. The black hole era is longer still. If the stelliferous era is 1 year, the black hole era is 10 to the 86 years. There is no intuitive analogy for this. The entire degenerate era is negligibly small compared to the black hole era. The 100 trillion year age of stars, the entire future history of every red dwarf that will ever burn, is negligibly small compared to the black hole era. No one expects these numbers to be emotionally intelligible. They are not designed to be. They are simply the consequences of the physics. But there is a specific realization that tonight's scale comparison is meant to produce. When we say the universe has a long future, we mean a future that is almost entirely empty, cold, and dark. The brief flash of the stelliferous era, the only era that contains anything recognizable as a world, is not a large fraction of the universe's timeline. It is an almost infinitesimally small fraction of it. The bright part is the exception, not the rule. Consider what this means for the question of life in the universe. Life on Earth required roughly 4.6 billion years of planetary history to produce anything like human civilization, from the formation of Earth to the current moment. A similar trajectory on a red dwarf planet, if red dwarfs can host habitable worlds, might require a similar timescale, or it might require more time due to the lower energy environment. But red dwarfs live for 10 to 12 trillion years. In principle, life could arise on red dwarf planets throughout most of the stelliferous era, not just in the small fraction occupied by Sun, like star lifetimes. If life is possible around red dwarfs, the great majority of civilizations in the history of the universe may not exist in any form we would currently recognize, because the great majority of habitable stellar lifetimes are still in the future. Civilizations like ours arising around Sun, like stars in the first 10 to 20 billion years of the universe's history, are not typical if red dwarf civilizations are possible. We would be, in the language of statistics, early arrivers. Absolutely no one anticipates this to mean we are unusual in any other sense. Early arrivers are still fully real participants. A civilization that arises on a planet orbiting a red dwarf 10 trillion years from now is not more legitimate than us. But it is a reminder that our reference point for the universe, the current 13.8 billion year old universe, with its mix of stellar types and its particular cosmic history, is not the only or even the most common setting in which the universe's full potential could be realized. Before we get started on the final section of tonight's story, there is one more comparison worth making. The time between the earliest life on Earth, roughly 3.8 to 4 billion years ago, and the development of human civilization, roughly 10,000 years ago, is about 4 billion years. The time between the Big Bang and the formation of the first sun, like stars, is about 1 billion years. The time between those first stars and today is about 12 billion years. All of this, the entire history from Big Bang to human civilization, fits inside the first 14 billion years of a stelliferous era that will last 100 trillion years. We arrived within the first 1/10,000th of the era of stars. If a future civilization arose in the last billion years of the stelliferous era, around one of the final red dwarfs, and if it developed technology comparable to ours and looked back at the history of the universe, it would observe a past 100 trillion years of stellar history. It would see a cosmos so old that the period we call ancient history, the first several billion years of the universe, would be as remote to it as the formation of the solar system is to us. The physics it would have to use to calculate the properties of very young galaxies would be as exotic to it as the physics of the early universe is to us. It is a different kind of civilizational perspective, and it would have a very different relationship to the question of tonight's episode. For that civilization, the time the universe has left would not be shorter than expected. It would be the final phase of a very, very long story. For us, at the very beginning, it is everything. The scale that tonight's story puts forward is not a reason for despair, but it is a reason for perspective. We are not at the center of cosmic time, we are at the beginning. And the beginning, in a universe with a stelliferous era of 100 trillion years and a black hole era of 10 to the 100 years, is a very specific and unusual place to be. After the last black hole evaporates, the universe enters the dark era. There is no other name for it that captures its character as precisely as that one. Dark. The dark era has no stars, no galaxies, no planets, no white dwarfs, no neutron stars, no black holes. It contains photons, neutrinos, electrons, and positrons, all expanding apart from each other in a universe that is cold and vast and structureless. No new structures can form, no chemistry can occur, no information can be processed. The dark era is the final state of the universe, and under the current best understanding of cosmology and physics, it is essentially infinite in duration. The dark era begins at roughly 10 to the 100 years. At that point, the density of matter in the universe is so low and the temperature so close to absolute zero that the universe is, for all practical purposes, as simple as it can possibly be. The laws of physics still apply, but there is nothing for them to act on that would produce complexity. Photons travel in straight lines across an expanding universe, receding from each other. Electrons and positrons, if they encounter each other, annihilate into photons. But in a universe of sufficiently low density, the probability of such encounters approaches zero. Individual particles effectively never meet. The question of whether the dark era is truly the final state of the universe, or whether something happens eventually even in the dark era, is one of the most philosophically interesting questions in cosmology. The answer depends on which physical processes, if any, operate on timescales longer than 10 to the 100 years. One possibility is quantum fluctuations. Quantum mechanics allows virtual structures to appear from the vacuum, and in a universe in thermal equilibrium, statistical fluctuations can in principle produce any configuration of matter and energy given sufficient time. This is the basis for the Boltzmann brain hypothesis, the idea that, given infinite time, a functioning brain, or any other organized structure, could spontaneously assemble from quantum fluctuations. The timescales involved are genuinely incomprehensible, involving numbers with more zeros than there are atoms in the current observable universe. But if the universe is truly infinite in time, these events will eventually occur infinitely many times. No one expects the Boltzmann brain scenario to be physically meaningful in any practical sense. It is a limit case-thought experiment, a consequence of applying statistical mechanics to an infinite time horizon. The important thing it illustrates is that the dark era, despite its apparent finality, is not a state of absolute eternal equilibrium. It is a state of extremely high entropy with tiny but non-zero residual fluctuations. The universe in the dark era is, in a technical sense, still dynamic. It is simply dynamic at timescales that make no human concept of time relevant. There is also the question of what dark energy does over infinite time. Current observations are consistent with dark energy being a cosmological constant, a constant energy density of empty space that drives acceleration without changing over time. If dark energy truly is a cosmological constant, then the expansion of the universe will continue to accelerate forever, and the dark era will be dominated by de Sitter space, a space-time geometry in which the accelerating expansion produces a cosmological horizon at a fixed proper distance, and within which a faint thermal radiation, analogous to Hawking radiation from black holes, is produced by the horizon itself. The de Sitter temperature is extremely low, far lower than the Hawking temperatures of the largest black holes, but it is not zero. In the dark era, the de Sitter horizon radiation may be the only remaining thermal process in the universe. Absolutely no one anticipates that these considerations can be resolved by observation. We cannot observe a universe 10 to the 100 years old. We cannot even simulate one meaningfully, because the timescales involved exceed any computation that could run within the universe's own lifetime, even with unlimited computational resources available. The dark era is a theoretical construct derived from extrapolating known physics over timescales that no physical process within the stelliferous era can test. But the derivation is grounded in well-established physics. The laws of thermodynamics, quantum mechanics, general relativity, and cosmology all point in the same direction. The universe is evolving toward maximum entropy. Entropy is the tendency of physical systems to move from ordered, low probability configurations toward disordered, high probability ones. The universe at the moment of the Big Bang was in an extraordinarily low entropy state, concentrated and hot and structured. Every process since then has increased the total entropy of the universe. Stars burning hydrogen to helium increase entropy. Supernovae increase entropy. Black holes accreting matter increase entropy. Hawking radiation increases entropy. The dark era, with its thin, uniform distribution of photons and leptons expanding apart from each other, is a high entropy state, approaching the thermodynamic equilibrium that the second law of thermodynamics predicts. Heat death is the informal term for this final state, and it is both accurate and slightly misleading. It is accurate in that the universe reaches a state of thermodynamic equilibrium, where no more work can be extracted from temperature gradients because no temperature gradients exist, where no more structure can form because there is no energy available to organize matter, and where the entropy of the universe has reached its maximum value. It is slightly misleading in that death implies an event, a moment when something stops. The dark era is not a moment. It is a state that the universe approaches asymptotically, coming ever closer to maximum entropy without ever precisely reaching it, because quantum fluctuations maintain a residual non-equilibrium at arbitrarily small scales. By the end of tonight, The dark era is where the universe's story effectively ends. Not at a dramatic moment, not in a collapse or an explosion, not in a clear final event, but in a gradual fading over timescales so long that no physical record of anything that happened before survives anywhere in the universe. The photons from the last Hawking burst, the final evaporation of the last supermassive black hole, will continue to travel through the expanding universe. They will be redshifted to longer and longer wavelengths by the expansion of space, their energy diluted across an ever larger volume. Eventually they too will be indistinguishable from the de Sitter horizon radiation, the faint thermal background of a universe driven by dark energy. And the universe will be dark. That is the answer to the question tonight's episode asked. The amount of time the universe has left is not shorter than you think, in the sense that it is brief. It is shorter than you think in the sense that the window of stars and planets and chemistry and life and complexity, closes earlier than the end of the universe. The universe will persist, in the most minimal sense of that word, for far longer than 100 trillion years. But the era in which the universe contains anything we would recognize, stars, light, the possibility of biology, that era is already more than 1% complete. We are living in the good part, the universe's bright, warm, structured phase, and eventually, even if the universe as a whole endures for a googol years or more, the phase we are living in will be long gone, remembered by no one, recorded nowhere, a brief chapter in a very long and mostly empty book. Tonight, we map the future of the universe. We started where we are now, in the stelliferous era, the age of stars. The current universe, 13.8 billion years old, full of galaxies and molecular clouds and the ongoing machinery of stellar birth and death, is at roughly 1/10 of the way through the total duration of the age of stars. The stelliferous era will last 100 trillion years. We are in the early hours of a very long day, and the rate of star formation that defined the universe's youth has already been declining for 10 billion years. We trace the shape of that decline, the peak of cosmic star formation at 3 to 4 billion years after the Big Bang, the exponential fall since then, the current quiet Milky Way forming only a few solar masses of new stars per year, where once it formed dozens. We talked about the red dwarfs, those faint, cold, enduring stars that account for 3/4 of all the stars in the galaxy, that will still be burning hydrogen when every star, like our Sun, has long since gone dark, and that will carry the stelliferous era forward for another 100 trillion years before the last of them contracts quietly into a helium-white dwarf and the age of stars ends. We entered the degenerate era, that vast expanse of cooling and dispersal that follows the last star's death. 10 to the 37 years, a number so large that 100 trillion years, the entire length of the stelliferous era, is a vanishingly small fraction of it. The white dwarfs and neutron stars and cold brown dwarfs of the degenerate era slowly cooling toward the ambient temperature of the expanding universe. The galactic structures gradually evaporating through gravitational relaxation, until even the merged remnant of the Milky Way and Andromeda has dispersed its stellar remnants into intergalactic space. The central supermassive black hole alone remaining. We talked about proton decay, that theoretical but physically motivated process by which the ordinary matter of the degenerate era could dissolve proton by proton into radiation and leptons, over timescales of 10 to the 37 to 10 to the 40 years. We talked about what happens if protons do not decay, the quantum tunneling, over timescales involving numbers with more digits than there are atoms in the observable universe, that would eventually reorganize matter into iron and finally into black holes. Either way, the endpoint is the same: black holes remain. We entered the black hole era, that penultimate chapter beginning at roughly 10 to the 40 years and ending at roughly 10 to the 100 years, a universe containing only black holes of various masses, each slowly losing mass to Hawking radiation, each growing hotter and more luminous as its mass decreases, until each one reaches its final evaporation burst. Stellar mass black holes going first, over 10 to the 67 years. Then the supermassive remnants of galactic centers, persisting for up to 10 to the 100 years. Each final evaporation burst releasing the energy of billions of suns in milliseconds. The universe's last fireworks in a sky that has been dark for incomprehensible lengths of time. We arrived at the dark era, the state after the last black hole has evaporated. A universe containing only photons, neutrinos, electrons and positrons, all expanding apart from each other, all cooling toward absolute zero, the entropy of the universe maximized, the arrow of time effectively erased. The de Sitter horizon radiation, the faint thermal signature of dark energy itself, the only remaining physical process in a universe that has lost everything else. And we looked at what it means for us, in the only era the universe has ever had that contains stars and planets and life and civilization. We are in the window, the brief, bright, warm window in the universe's long history, during which matter can form planets, and planets can sustain chemistry, and chemistry can sustain life. Not the only window, perhaps. Red dwarfs may extend that window by another factor of 1,000. But even 10 trillion years is a window, not an eternity. The universe's total future is enormously longer than any window it offers for complexity. That is what shorter than you think means tonight. We did not say the universe is ending soon. We said the good part is shorter than you think, the part where there are stars to navigate by, oceans to cross, planets to stand on, skies to look up at. We are in it now. Every night sky you will ever see is a sky full of stars that will not be there forever. Not gone in your lifetime or your children's lifetimes, or the lifetimes of anyone you can imagine, but gone, eventually, cooling, dispersing, fading, and what follows is long and cold and dark and quiet. Sleep well tonight. The stars above you will be there when you wake up. They have been there for billions of years and will be there for billions more. The universe's long night is still unimaginably far away. You are here in the bright part. Good night.